Welcome to Differential Equations, a guide for teachers. This is a re-recording owing to technical difficulties during the online conference. So my email address is there and I welcome any correspondence, and you can get the slides from the address shown. Also, the scratchings that I refer to there was not the scratching of the dog you just heard. The scratchings I refer to are things that I handwrite later on, which will make sense. You'll probably want to get a copy of those. So just to cover what we're doing today, the presentation conveys concepts and demonstrates skills. It's not like a pedagogical introduction from beginning to end of how you teach this in class and so on. The audience is for teachers who, maybe they've taught this already and want to see how someone else looks at the topic. Maybe they're teaching it sometime soon or might be. And basically you should come away understanding differential equations better than you walked in. There's no need to write anything because everything that I write will be available later. We do cover easy, medium and hard in this presentation. And we're looking at sort of big picture mixed with little details rather than, like I said, this is how you might tackle it with students. There's an interesting example at the end that could possibly have run out of time in the conference, but I don't have that limitation now, so we will include that. Here are some resources. So in 2020, I recorded a series of classroom lessons and put them on YouTube and made them available to the community. This was at a time when schools were largely in lockdown. It was the first time I was teaching the topic, and I felt like I needed to do a really good prepared job for the students. So that's what I did. So those are available to you. You're welcome to use them, welcome to show them in class. There are lesson notes available for printing. Other teachers have learnt the topic from this and so on, and that's fantastic. It is my first attempt at it. It's aimed at students and it's a bit rough around the edges in places, but it's a good body of work. Hubert Lamb booklets are always good value, of course. If you go onto MathLinks and search differential equations, I'm sure you'll find them. Joel Speranza videos, it's become known to New South Wales teachers more recently. I believe he's from Queensland. Very good video presenter. So if you go to his website, which is linked at the bottom of the page, and then follow that trail through New South Wales, Extension 1, etc., you'll find your way to differential equations. And I haven't watched them all, but they certainly appear to be well sequenced and well presented. There's an online course if you want some PD in differential equations. So it's a long online course, very thorough, very detailed. So that's commercial. It's all created by me in conjunction with Stuart and Richard at PD for Maths. So that's available too if that's something that you would be interested in. Okay, so we'll start by looking at some simple examples where I'm not handwriting anything. We're just getting a sense of what's going on. So y dash equals x cubed plus 2x is a differential equation. And it has this solution. Now that's a very easy solution to find. All you have to do is integrate with respect to x. Remember to throw in the plus c. Okay, c is a constant. So we have a family of solutions here. So what do we learn from this really simple example? Well, a differential equation is an equation that involves a derivative. That's really as simple as it gets, right? The solution of a differential equation is a function. So when we solve equations before learning this topic, we expect to get either a number as a result, or perhaps 2, 3 or more numbers, or maybe an algebraic expression if we're solving a literal equation. Well, with a differential equation, our aim is to find the function that makes the equation work. And in the case above, it's a family of functions. There are infinitely many functions there, but they only differ by a constant. Y dash equals sec squared x with y of pi on 4 equals 3, well, this is an initial value problem. It's a differential equation, but we have a piece of data. So it has a very specific solution, y equals tan x plus 2. So we don't whack on a plus c, or in the working, we can whack on a plus c and then find the value of c, and here we go. So the solution of an initial value problem is a specific function, not a family of functions, because some data is known that nails it down. So poetically, I can say that all the previously infinite possibilities have converged into one outcome. You can type differential equations into Wolfram Alpha. I encourage you to do so. So there's our first example. It shows how it's interpreted it, and it's made it clear that y dash is a function of x. Right, and there it is. And here's our constant, and there's our quarter x to the 4 plus x squared. Here's our second example. So I've given this is all just typed into Wolfram Alpha. I've given the initial value. Note that initial doesn't have to mean t equals 0. It's just the data that we initially know. Right? It's shown how it's interpreted the input, and it's interpreted it all beautifully. And here's the answer. This is something else that comes up in Wolfram Alpha's output. And this is vocabulary that we need to be comfortable with, but I'm not going to heavily emphasize here. But a quick breakdown. Differential equation, you know what that means. Ordinary, well, differential equations break into two groups, as far as I know. Ordinary differential equations and partial differential equations. Partial derivatives are something we don't tackle in high school. That requires calculus of several variables. So if it's not partial, then it's ordinary. So everything we do is an ordinary differential equation. Linear means that the derivative has not been squared or raised to some other power or whatever. And first order means that only the first derivative is involved, not the second, not the third, and so on. And I'll just throw in here a sales pitch for differential equations, like why do we care about them? Well, science would stand still if it weren't for differential equations. So differential equations are making a statement about the rate of change of something. And you may not have formerly been aware that in science it's often easier to analyze how something is changing than what it is. So we tend to make the mistake in mathematics of saying, all right, so the displacement of some particle is given by blah, 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 x equals t cubed minus something t plus 1 or whatever, right? And then we find the velocity and the acceleration. Now, I call that a mistake. I mean, it's obviously it's mathematically valid, but scientifically, you tend to first be able to analyze the forces that are acting on something, and that means that you're finding the acceleration. And that's a differential equation. And it might be a really simple one, or it might be complicated. And that differential equation, from that, you work your way towards describing what's actually happening. It's the same with something like spread of disease. It's modeled with differential equation, like how are things changing, right? What's the rate at which people are becoming sick? What's the rate at which sick people are recovering? What's the rate at which people are dying? These things are actually all they are all interdependent, right? In a fixed population, your probability of getting sick changes with how many other sick people there are, right? It's not just some function of time, it's some function of other things, right? They're all intermixed, they're differential equations, and then you use techniques beyond high school to solve those differential equations, and then you can plot graphs that make predictions about how many people are going to be sick in 2 weeks' time. That's the heart of mathematical modelling. Okay, simple example number 3. Y dash equals ky is a differential equation. It's a bit of a weirder one because it doesn't have an x anywhere. But this one we know to have the solution y equals ae to the kx. So this is just exponential growth. And we know that because it's in the syllabus, right? But if someone just plopped down y dash equals ky in front of you and you hadn't learnt it before, you'd rightly think it's weird, and therefore students have a right to think it's weird. Now, we can verify this by differentiation, and students are routinely asked to do that, but we might feel uncomfortable solving it by integration. So that's what this topic of differential equations brings to the table, right? We can go both ways in this, and we'll do that in this session. Right, slope fields and solution curves. So mentioned differential equations to a New South Wales maths teacher a few years ago when it was known that it was becoming part of the new syllabus, and quickly get a reaction, oh dear, what do those slope fields mean? Oh, we're going to have to teach those slope fields and so on. Well, luckily they're actually very straightforward. So here's, well, y dash equals x cubed plus 2x. Here's a slope field for it. So we have an xy plane, and this is rather discrete. Okay, we've got a few hundred orderly chosen points here, and at each point, so I'm highlighting one here which is like 1, 2 roughly, and it's telling us that the gradient, well, we can visually see the gradient. I'm sort of tracing it out. I could estimate that to be a gradient of 4 or something like that. Okay, so the slope field is telling us that the gradient at this point is, let's just say 4, whereas the gradient at this point is practically infinite. The gradient at this point looks like about a half or a third. Gradient at this point looks like about negative half, say. But the thing is, there's no curve anywhere, so how can I possibly be saying the gradient at this point? Well, this is where the solution curve comes in. So if you choose any point, if you have a slope field plus a point, you can trace out a curve, okay, because the curve has to obey the slope field. You can see here, the curve goes through there at the gradient indicated by the slope field. Right, the curve makes its way through these slope field indicators, or I like to think of them as like iron filings. Right, the curve makes its way through them without crossing any of them, because if it crossed an iron filing, it would be disobeying the rules which says that if you go through this point, you must have this gradient. So a slope field, let's go back, a slope field is allowing us to imagine infinitely many curves, okay, and it's suggesting those curves to our eyes. And here are just 2 in particular with chosen initial points. Okay, so those were done in Geogebra, and here are the instructions to get them going. So you start off by defining your function, and best to define it in terms of x and y, because a lot of functions have x and y in them. Right, this one doesn't. And then type in slope field, comma f. Right, it'll give it this name automatically. Don't care about the name. I've defined 2 points just by typing them in, or you can use the point tool. And then I just type in solve ODE, so Geogebra knows about this, solve ODE bracket f comma a. So we're identifying the function, which is our gradient function, and we're identifying the point. Now, if you want to be classy, you can actually call this function f dash, because then it looks really cool here because it's a gradient function, so it's f dash comma a. I just forgot to do that. So it's analysed that, and it's come up with a particular equation. So it's basically solving an initial value problem here, and it's graphed it, right? And that 11 over 4 is 2.75, and you can see like the constant value there, about 2.75. And then here's the same thing, but just with a different point, right? So anyone can create these. It's not difficult. Of course, it would be difficult if you didn't know how, but if you just keep this screenshot with you and just remember that this is about typing things in, and you don't type that in. It wouldn't kill you if you did, but you don't type that bit in. Geogebra will fill that in for you, but you do type all of that, just that, and you'll get what I've got here. Right, now just be careful that you're using a suitably powerful GeoGebra, not something like a geometry calculator or something. you want to go with Geogebra Classic version 6. Here's the second one, y equals sec squared x with the given data, and not surprisingly, it gives us a tan graph in return. Okay, let's get into the spirit of differential equations. So this is something I learnt from a MANSW conference years ago, and it's when I first understood this slope field in business. So what's it all driving at? Let's see. So we're looking at an example of cooling. We all know about Newton's law of cooling. So an object is removed from an oven and placed on a bench to cool. The ambient temperature is 20 degrees Celsius. The differential equation that describes the rate of change in temperature over time is as follows. Now, I've got k equals 1 here. Just think k could be any constant, but I do have a graph here, and that needs to have a particular value of k. So just excuse that being so specific. It's really just any constant. Now let's pick this apart. In the past, students may be presented with this, and then part A show that t equals blah 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 satisfies the differential equation, and that's as far as they'd get into the topic of differential equations. Now it's really important, I think, that we understand what this is actually telling us. So dt is the change of temperature over time. Now k is a positive constant, so the fact that there's a negative here is telling us that this change is likely to be a negative one. That is, the temperature is decreasing. Now capital T is the temperature. There's no mention of time here, right? Because the change in temperature does not depend on the clock on the wall. The change in temperature depends on what the temperature currently is. And T minus 20 is like the surplus temperature above room temperature. So think of it like the relative temperature. Okay, if something's removed from the oven and it's 140 degrees, and really it's only like you get 20 degrees for free. That's room temperature. So really you've only got 120 degrees, something like that. So basically, the bigger they are, the harder they fall. So the more surplus temperature you have, the greater the rate of change is, although it's negative, right? And then if your temperature is only just a tiny bit above 20 degrees, then this value here is tiny, right? It's close to 0. And so your rate of change is close to 0, because you can't be like plummeting down in temperature if you are 21 degrees and the ambient temperature is 20 degrees. You can't go crashing through that. That just wouldn't make sense. Right? You're reaching an equilibrium with the environment. So everything about this can be explained. And later on in this session, we're going to derive from this. Okay, we've said nothing yet about an initial temperature. So, from the information we have so far, we can get a slope field. And the dotted line just shows the ambient temperature, and the slope field indicators are all flat there. Now, we have temperature on the vertical axis and time on the horizontal axis, right? But nothing to do with this was about time. Okay, now we get some more information. So the initial temperature was 100 degrees, and there we go. We've got an initial value that can go on. We can get a solution curve. Very cool. Scenario 2, the initial temperature was 70 degrees. Well, you can see both of them side by side, both converging to the ambient temperature. Scenario 3, the person who took the object out of the oven didn't know they were supposed to take its temperature. When I walked in and realised this 5 minutes later, I measured the temperature to be 85 degrees. Well, that's 0.3 there, right? It's 5 minutes here and 85 degrees here. And we can even trace time back here and find that the initial temperature when it came out of the oven must have been, it looks like, about 125 to 130 degrees. So initial doesn't have to mean on this axis, right? Scenario 4, plot twist, the oven was never turned on and the object was actually frozen. All we know is that when T equals 3, the temperature is negative 10 degrees. So that's down here, right? So T equals 3, negative 10 degrees. So we're actually warming up, because that T minus 20 is actually negative now. And so the negative k times a negative number gives us a positive, so our rate of change is positive, right? And it's equalizing towards room temperature. Now change the value of k. I'm not doing a dynamic component here, but if you put things into Geogebra, if you change the value of k, then all of your slope field indicators will wiggle around and all your solution curves will follow the orders given. Okay, that's a very good thing to do. All right, comprehensive examples. We're about to get algebraic. So we've been pretty conceptual so far. We're about to get algebraic. So first example, with no physical context, y dash equals negative x over y. There are a few questions. 1, what does the slope field look like? 2, verify that y equals square root of r squared minus x squared, which is a semicircle, satisfies the equation. And that means start with the equation and end with the differential equation. Okay, that's a verification. 3, solve y dash equals negative x over y. That means start with the differential equation and end with something that looks like y equals square root of r squared minus x squared. Part 4, solve the two initial value problems. So just those two, the same differential equation, just with two arbitrary chosen points. Okay, so I'm going to handwrite answers to these in a minute, but first we're going to take a broad look at example 2. So this is the temperature one that we just looked at. So first question, well, we've already seen the slope field, so I won't be looking at that anymore. 2, we're going to verify that this familiar kind of equation, temperature equals 20 plus AE to the negative k times time, satisfies the equation. So that, once again, means we start with the end and work towards the beginning. 3, solve the differential equation, so we start at the beginning and work towards the end. And 4, and I won't actually do this, this is just a Year 11 Extension 1 question, not the topic that we're doing today, but just acknowledging that this is an initial value problem with an extra kick, because we have to find the value of k. So find the equation of the temperature over time, given it was initially 85 degrees and 10 minutes later it was 52 degrees. All right, so it's time for me to do this as an exercise, which means I'm going to my iPad and I am writing. Well, let's just test the tools here. Yep, I'm writing, and I'm going to start that in 30 seconds after I've had some water. Okay, sorry you had to wait. Now, question 1, what does the slope field look like? So of course we could ask Geogebra, but this is an important thing for students to do, and that is to work it out themselves. So what I have here is a grid of discrete values. These are x values and these are y values. And we're going to fill this in with numbers. So I'll just write it out, right? Y dash equals negative x over y. And it is y dash that we're evaluating and putting in all of these. Okay, we are not evaluating y values, we are evaluating gradients. And interestingly, the gradient depends on the x value and the y value. Right, so I'm going to, right, what I'll do, I'll start, if you like, naively, and just do a couple by raw calculation. Right? In fact, I'll do one, and well, let's just take this one, okay? So if x equals -2 and y equals +3, right here, then and y dash equals -x over y, then that is -2 over 3, which is simply 2/3. Okay, so I'm going to pop a 2/3 in there. Now, of course, I'm not going to be this painstaking about every item in this grid, right? But just need to emphasize the calculation that goes into each one. Right. What have we got here? We've got -3 and +3, right? And that, when you work it out, is 1, right? And then that gives me an idea. This will be 1 as well, because it's like -2 and +2, right? And then we've got this negative as well. And then this will be 1 as well, right? Now, careful about 0 over 0. That's undefined. Right, what about, and I think we'll have 1 down here and 1 down here and 1 down here. Okay, let's just sort of do a sanity check. So I've got 3 over -3, but then the negative out the front. So yeah, all right, I'm being sort of deliberately slow here. Right, so now while I'm being smart about it, well, let's note that y is in the denominator, so we can't have y equals 0. So I'm just going to cross all of those out. Can't have y equals 0. And what else have we got here? Well, x is in the numerator, so when x is 0, then this whole thing is 0. So I'll put zeros wherever x is 0. All right. Now let's do some negative ones. So this one here is 1 over 1 is 1, but there's a negative out the front, so that's -1. And likewise these ones are -1, and likewise these ones are -1. And what about this? We've got 2 over 1, right, but with a negative, so that's -2, and then this is 3 over 1, so -3, right? What about this part? 1 over 2, but right, negative, and this one 3 over 2, but negative. This one 1 over 3, but negative. This one 2 over 3, but negative, right? And I'm now ready really to mirror this everywhere, okay, because it's such a symmetrical kind of thing here. The only thing that changes is the sign. So these negative ones will be mirrored down here, because here it's like x and y are both positive. Here x and y are both negative. They cancel each other out. So just mirroring them, get the -1, -1/2, -1/3. This is -2/3, right? -1, -2, -3. Let's just double check every now and then. So, yep, that over that. Yep, that's right. Okay, and the last one here, -3 over 2. And this is 3 over 2, 3, 2, 1/2, 1/3, and okay. So when filling out something like this, you can use as much or as little pattern matching and so on as you like. use as much or as little raw calculation as you like. Now this is all a precursor to a slope field. This is not the slope field, and so I'm going to do the slope field here, but I'm just going to take these values with me. And I want them to be really light because they're the background now, not the foreground. All right, so I'm going to put in gradients now. So 0 is a very easy gradient to put in, so I'll put in all the zeros that I can. Okay, 1's very easy. It's like a 45-degree angle, right? There's lots of these 1's. -1, that's okay. It's pretty easy. Okay, now I should try to be careful with these because we now have to try to distinguish. So in that spirit, I'm going to redo this one. I don't think I was careful enough with those three. Okay, and especially with, like, that's a gradient of -1 right there. You can visualize it. So try to get them right. Okay, now we've got to try to get a 2, right? So, of course, a gradient of 2 is across 1 and then up 2. So, like, that. But, yeah, that didn't quite cut it. So you just try to do it as accurately as you can. It's never going to be perfect. And then steeper still for 3. That's about all you can really do, is just try to make it a bit steeper as you go. Right, half is not too bad. No, that wasn't so great. Maybe, okay, 3/2, 2/3, 1/3. Okay, -1/2, -3/2, -2/3 maybe, -1/3. Okay, -1/2 here, -1/3, -2/3, -3/2. Right, feel like I'm starting to get the hang of it. Okay, there we go. Now these ones, so clearly it looks like, oh, I missed one. It's half. Right, so clearly it looks like some kind of whirlpool, really. Okay, if you were a charged particle and this was a magnetic field, like, you'd be doing that sort of thing, right? Now these ones here, they actually deserve, these are vertical, and I'm going to say something about that. Okay, but not the one at the origin. So there's a difference between, say, k/0, where k itself doesn't equal 0, right? That's vertical. And 0/0 is, which I believe mathematicians call it, indeterminate. Okay, and so if you have a gradient that's a k/0, then you can apply limiting ideas, like you can say, k/x as x approaches 0. Okay, now that approaches infinity, right? So that's why we get these infinite gradients. Right, now I'm just being loose with notation there, just try to give the idea. But 0/0 doesn't have that feature. Okay, so clearly, now coming up, of course, is looking at semicircles. So look at that, we clearly have semicircles going on here. Right, so now we'll get into the algebra. Oh, and by the way, here's a GeoGebra rendition of this very slope field. Okay, y' equals -x/y. So in GeoGebra, you'd be typing, say, f'(x, y) equals -x/y. I mean, it lets you type in a good-looking fraction, and then you just type slope field, f', that's the only argument, so that, and then the slope field, and then just put in a point A, which you can, do by typing in or use the point tool, and then solve ODE f' comma A, right? And then this will appear, and if you move A around, then it'll change the solution curve, and if you put A down here, you'll get an upside down one, okay? All right, into the algebra. Now this is going to be fairly quick, right? This is like meant to be part of an hour-long presentation. I don't want to take all of your time, but it's also, you know, you're just meant to come away with the idea here if you haven't seen it before. You'll only really get good at it by practicing. Okay, so verify that y equals that. So we've got y equals, that's r squared minus x squared to the power of a half times negative 2x, chain rule. And this is y dash. Y dash equals, okay, all right. So I said I'd be quick and then I made mistakes. Isn't that always the way? All right, let's be clear. That's what y is. And now y dash, if I differentiate it, is half of that, right, times negative 2x. We get a bit of cancellation here. And so we're left with negative x over square root of r squared minus x squared. Right, but this denominator is just y. And so we've got y dash equals negative x over y. Done. Right? That's what we were expecting. Satisfies the differential equation. Right? Not something we normally do. Well, this is the new normal. Okay? And number 3, to solve y dash, so to go the other way, and here's just a bit of discourse I like to give students. Okay, so this shows that, like this working here, shows that this does solve the equation, but could other things possibly solve the equation? Could there be other functions that don't look anything like that that also solve that, right? So it's important to settle that question, and to do that, well, we need to start at the source and work outwards and find that we actually end there and we don't end anywhere else. All right, so it's important now to write dy dx instead of y dash. And what we can do is separate these, right? So I can cross multiply, so I get, I get y dy equals negative x dx. Okay, now if that looks weird, okay, it's all right, you get used to it. I think mathematicians call these individual bits differentials, right? And this is a perfectly valid thing to do. Extension 2 teachers would be used to this from old volume questions and that sort of thing, and it can come up in mechanics. But we did all that without ever like really studying differential equations in the past. So anyway, this is a valid mathematical statement. It still is. This is a statement about how y changes with respect to x. Well, this is also a statement. It's about how it relates the change in y to the change in x. Okay. We can proceed by taking integrals. I'll bring the negative out. Okay, we proceed by taking integrals. Now, I feel a bit weird about whacking an integral sign in front of something without having to put that there because it's already there. To me, it feels like kind of this is a left bracket and this is a right bracket, and you don't add a left bracket to something without also adding a right bracket. I'm not going into it now, but there are ways you can break this down like further to be really satisfied that what we're doing here is legitimate. In fact, the topic guide has something to say about that. Okay, take these integrals. Half y squared equals negative half x squared plus c. Okay, and I'm going to do something now that will cause some people to have a bit of an allergic reaction. If I double it, I get y squared equals negative x squared plus c. All right, just make the point that 2 times an arbitrary constant equals an arbitrary constant. Okay, until I actually evaluate C, I can call it anything I damn well please, and I do not need consistency from this line to this line. And I'm not evaluating this, I'm just getting a general solution. Now this gives us x squared plus y squared equals C, and I'm pretty much, I'm going to leave it there. Okay, so that's why I said we got something like y equals the square root of r squared minus x squared. Okay, we've actually got y equals plus or minus the square root of c minus x squared, but that is something like this. Now why this and not that? Well, because there's literally no difference between them, and this looks nicer. And the fact is, until we have a data point to substitute in, we don't know if we're dealing with an upper semicircle or a lower semicircle. And you could reasonably ask, well, we'll get into we'll get into these now. So question 4. All right, so if I've got y dash equals negative x over y, well, that implies that x squared plus y squared equals c, no other solution, right? That's from above. And now if I substitute 3, 7, substitute 3, 7 to find c, then what I get is 3 squared plus 7 squared equals c, or c equals 58. And so therefore x squared plus y squared equals 58. Now, tempting to leave it there, but should ensure your answer is a function, if possible. Okay, now I don't feel really qualified to adjudicate on this, but I've taken advice, and I think that the solution to a differential equation should be a function. Okay, so we'll get y equals plus or minus the square root of 58. Actually, I'll be a bit more explicit. So y equals square root of 58 minus x squared, or y equals square root, negative square root of 58 minus x squared. Okay, and this one satisfies 3, 7, which is the one thing we know about this, and this one doesn't, right? So therefore, y equals square root of 58 minus x squared. Okay, and in the other case, which I'm not going to do in full, given sub 8 comma negative 2, right, we'll end up with y equals negative something, because 8 comma negative 2 is below the x-axis, right? So so these will be the other way around in that case. All right, let's move on to example 2. Okay, so we've seen the slope field, so we're not looking at that again, but just remember that there was this ambient temperature, and like the solution looks like that, right? And all the slope fieldy line things, kind of indicate solutions like that. Okay, so number 2, verify. So this is easy. All right, so t equals 20 plus a e to the negative kt. All right, so note t minus 20 equals a e to the negative kt. I'm going to call that equation 1. All right, and now dt equals, well, the 20 plays no part, so we've got a times negative k e to the negative kt, and I'm going to rearrange that to put the negative k at the front and put this in brackets, right? And that is negative k lots of t minus 20 by equation 1. Okay, now call me a purist, but I think in an exam, if you're asked to show that this verifies, then you've got to be really explicit in showing that it is, and not just fudging, or not just giving an answer that looks like you could fudge your way towards a result that was actually given to you. Okay, I think most maths teachers agree with that sort of idea. It's just this is a good way to put it into practice, right? By making this observation up front and then referring back to it. Okay, so that's a verification done. Tick. Now, for the new part, how do we solve, right? So how do we solve this differential equation? dt equals negative k outside t minus 20. Right, well, there's a couple of ways to go about this. They're really the same in the end, but something we can do, well, we can separate the variables, right? And that means that we want to get this with this, and there's no t over here at all, so this is going to be by itself. I think I'm going to demonstrate that way because it's consistent with what we did before. So we'll get dt over t minus 20 equals negative k times little dt. Now, just want to demonstrate something here. I'm keeping the constant with the independent variable, and I did that in the last one as well. Okay, that's deliberate on my part. I want my dependent variable that I'm solving for, I want that to be uncluttered. Okay, and so we've got okay, we can bring in the integrals. All right, this is log of absolute value t minus 20. The absolute value is kind of important. Kt plus c. Now I don't have any value to put in at the moment. This is a general solution. All right, and even with this, there's too much information there that I probably wouldn't be putting it in. So, so what am I going to do? Well, I'm going to now take I'm going to do the exponential of these, right, to get rid of the logarithm. Right, now I've got this plus c. Now watch what I do with it. Okay, so I've got absolute value of t minus 20. Right, just note please that t, as we saw before, can actually be a negative value, and t minus 20 can be a negative value, right? So if we want to account for all scenarios, we need this absolute value. So this is e to the, well, it's e to the negative kt plus c, which is e to the negative kt times e to the c. Now, I don't care if c is positive, negative, purple, or green. E to the power of c is greater than 0. So this is capital A e to the negative kt, where capital A equals e to the c, and it's strictly positive. Okay, so there's actually a bit of subtlety going on here that really can't be avoided. I don't want this absolute value to hang around. Okay, so I'm going to deal with that now. Okay, so now, right, so if we deal with the absolute value, then what we get is t minus 20 equals plus or minus a e to the negative kt. Right, now notice, of course, that a is strictly greater than 0, but we've got a plus or minus now, right? And that actually means that I don't want that, okay? And just like I could double C before and still call it C, I can still call this A. I'm just noting the restrictions change, right? So now notice how I don't have A equals 0 here. Now that actually comes in, right? And this is getting very subtle. So observe that t equals 20 is a constant solution of our differential equation. Now, if your eyes are watering and your brain's going funny, I don't blame you, all right? So I've thrown this in here, but let's see. Let's see what this means. If t is 20, then t minus 20 is 0, right? And so this whole right-hand side is 0. But guess what? If t is 20, well, the left-hand side is 0 as well, because it's just like a constant, right? So all the textbooks cover this, right? So you're not going to get through the topic without it. Yeah, it's important when you get things like this to look for a constant solution. And so, and what that means, right? So that means that A can equal 0 as well. All right, so here I've got A can be positive or negative. Well, now I'm saying A can be 0 because t minus 20 can actually be 0. And that's never going to be 0. So the only way the right-hand side can be 0 is for A to be 0. Okay, so therefore t minus 20 equals A e to the negative kt, where A is any real number, right? Positive, negative, or 0, i.e. t equals 20 plus A e to the negative kt. Right, and that's what we were asked to find, and we found it. All right, so it's very nice mathematics. This is all a bit complex, and a student who's deriving this, say, in an exam, is not expected to produce as much detail as I have here, but of course it's important in the teaching. Okay, so we've done this, right? And I don't even need that page, and right, and that comes a bit later. Okay, so now we get into slope field matchup. It's a really important skill in this. It's not going to take long to cover. Right, so I've got some slope fields here. We need to match 4 slope fields to 4 differential equations. You're welcome to pause and give it a crack. I'm going to march on. This first one, what do you notice? Well, I notice that when y equals 1, the gradient is 0, right? So dy dx equals 0 when y equals 1. Let's go over here, and none of the others have that feature, right? Okay, so let's go over here and look at that. When y equals 1, this whole thing will equal 0. So there you go. I've matched 1 to d already. It must be it. I haven't looked at any other features of this, and like it's actually really good too. I'd just like to point out this gradient depends on y only. It doesn't depend on x. And when you look at this, you can see that at any given y value, all the gradients are the same, right? At any given y value, all the gradients are the same. X plays no part. Okay. Right. Next one. Oh, well, this is kind of the opposite. When y is negative 1, then dy dx is 0. And that's this one, because if you factorize x, y plus x, then you get x outside y plus 1, right? So this will be 0 when y is negative 1. All right, so I've matched 2 of them. What have we got here? Do we have any 0? No, I need to do something else here. So I can observe that when y equals 0, we have vertical gradient, so dy dx is undefined. There we go. Right, we've got y in the denominator there. And so that looks to be like, so 3 goes with a. And if you look here, x minus 1, so when x is 1, then the gradient will be 0. And lo and behold, when x equals 1, the gradient is 0. Okay, so a gradient function like this gives you a more, varied kind of slope field, rather than the exponential and the circle ones that we've seen. This one's exponential, of course. And last one here, well, we've got process of elimination, but I'd just observe that when x equals -2, we're looking for undefined when x equals -2, and we get it there. Okay, so you should be bringing a lot of sophistication to your analysis of these questions. All right, this one's from either real HSC or sample HSC, I don't remember. First observation before I even read what the options are is that in the first quadrant, it's always negative, and whether it's positive or negative depends only on what quadrant it's in. So first quadrant negative, so remember x and y is positive in the first quadrant, and if you just look at that one, if x and y are both positive, then this gives a negative, right? And maybe same with that one. Okay, but these, if x and y are positive, you get a positive value. So I've knocked out a and c. So now is it x on 3y or is it xy on 3? Well, you can just maybe try a point. You can pick a point like 4, 1, say. Okay, 4, 1 looks to have a gradient of roughly -1. Let's see, does that work here? Well, yeah, okay, maybe I haven't picked the best one. 1's too nice a number to work with multiplication and division. Let's try 4, 3. And look, there's probably a better way of doing it. What about this? We seem to have y dash equals 0 when x is 0. I guess that's true for both of them. All right, when y equals 0, if we looked at that, if it was this one, then we would have vertical gradients all along here, and we don't, so it's not that one. Okay, so there you go, it's this. And you could probably find some other reasons why it is too. And in class, you should be looking at these in as much detail as possible, not just answering and moving on. Okay, this is obviously not HSC style, but I just like the diagrams too much, and there's a indication of where I got them from. This presentation risks going over time, so I just encourage you to have a think about those yourself. Okay, here's our last thing. Concentration of salt in a stirred tank. So this is very cool, but it's not clear that this will ever be assessed in New South Wales. It's also not clear that it won't be. It's one of those things where we won't know until one day it just appears in the HSC. NESA cruelly did that to us in more than one course last year. Who's to say they won't do it again? So, but this is from VCE, and it makes me think that if VCE do differential equations and they include this, then why shouldn't New South Wales? Of course, not every argument is that simple, but I would just be afraid of not, I've never taught it to students, but that's just because I ran out of time. I'd just be afraid of not ever teaching this and not building some awareness, and good for teachers as well. Okay, so a tank initially has 20 kilograms of salt dissolved in 100 litres of water. Right, pure water flows into the tank at a rate of 10 litres per minute, and the solution of salt and water, which is kept uniform by stirring, flows out of the tank at a rate of 5 litres per minute. So before we get any more information or get asked any questions, let's just build a mental image here. There's a tank of water. It's got 100 litres, 10 litres a minute coming in, 5 litres a minute going out. So the amount of water in the tank's increasing. So hopefully it's got, a lot of spare room. Secondly, the water coming in has no salt in it, and the water going out will have salt in it. So the amount of salt's just going to decrease over time. And in fact, if this experiment were run for years, then you'd expect to be able to drink the water quite comfortably in the tank after a long period of time, right? Because there's no salt coming in. So it's probably heading towards 0. All right, so here's an actual question. If X kilograms is the amount of salt in the tank after T minutes, show that the differential equation relating x and t is as given. Okay, so now if you scour the New South Wales syllabus, then this question is arguably askable, okay, because it's about understanding. I can't remember the chapter and verse, but it's about like modelling, right? And B, find the amount of salt in the tank after 30 minutes. Right, so I've adapted this from a VCE question. The real question went on to like part. I've changed like these. I've changed it already, but it goes on to be even harder. Okay, so now ready to give this a go. All right. So I'm just going to, draw a. Right, so we've got 100 litres. Well, we've got 100 litres initially. We've got 10 litres a minute coming in, and we've got 5 litres a minute going out. As far as salt goes, well, we've got 20 kilograms of salt, right, dispersed amongst all that water, and it's kept uniform by stirring. Okay, so we're being asked to find something about the rate of change of salt over time. Now so the change in salt over time, well, it depends on the inflow and the outflow. Right, so let's look at the change coming in. Now it's actually that's actually really kind of simple. Well, I suppose I might just use equals for this. That is that's 0. There is no change to the salt occurring because of what's coming in. All right, now a change in the question, which the original question has, where this was actually partially salty, well then that would then have an effect on this. Okay, but the change in salt there is 0. Just checking my notes, because if I ever do something wrong, it means I have to re-record. Okay, and another thing I like to do is, make my units explicit. That's kilograms per minute of salt, right? dx dt is in kilograms per minute. If we make the units explicit, then we'd be more confident that we're answering the question correctly. Okay, the change going out, well, it's a negative change, and it's we've got X kilograms of salt here, right? And it's the amount of salt divided by like the quantity of the solution, and that varies with time. Now that is in kilograms per litre, right? And then to get kilograms per minute, we need to multiply by the 5 litres per minute. Okay, now that's really messy. I'm sorry about that, but yeah, we have that times that. Okay, and kilograms per litre times litres per minute, the litres cancel out, which gives us kilograms per minute, which is how I know I'm doing the right thing. Now I kind of meant to say up front QT equals the quantity of solution in the tank, right? The unit for that is litres. And it's really simple observation that Q of T, well, it starts at 100 and it goes up by 5 litres a minute. So we've got our 5 litres a minute times minutes gives us litres, plus litres is litres. Okay. So this is negative x, or I can multiply by the 5, negative 5x over, now I've just realised, I'm sorry, I am going to remove the negative from here and bring it in later instead. Okay, so 5x over 100 plus 5t, and that is kilograms per minute. Okay, and that we can divide through by 5, so that's x over 20 plus t, which is encouraging because that's what we've got there. Okay, and now the overall dx dt, well, it's the inflow minus the outflow. Okay, so I'm thinking of this as kind of a directionless quantity, you know, rather than being positive or negative. I'm just describing the change. And now, if I want to look at the overall, then I just say, well, treat in as positive, like how much salt is coming in, and then subtract how much is going out. All right, so that's 0 minus x over 20 plus t. So therefore, dx dt plus x over 20 plus t equals 0. And that's what was required. Okay, now there's no real benefit to expressing it like this, I don't think. Right, we could have just got rid of the 0, of course, and had dx dt equals negative that. That's what we're going to use in the next part, but I think if you look at the original, like any VCE question, and find a complicated one like this, you'll find that it develops in a way that kind of, you know, bases itself on that. Okay, and so that was part A, and now B, so find the amount of salt in the tank after 30 minutes. So we get dx dt equals negative x over, I'm just going to write t plus 20. And so to proceed here, we need to separate the variables. So I get dx over x equals negative dt over t plus 20. Okay, so I've separated the x has gone down, t's gone up. I'm keeping the negative with the independent variable. Right, so okay, lazy students and teachers won't do 2 lines here, right? They might write that down and then they'll throw their integrals in. I think it's good to give this line its due. That's just me. All right, so dx over x, so I'm going to take ln x, I'm not going to do absolute values because x and t, or t plus 20, are both positive, right? So the absolute value just simplifies immediately. And then, right, we're going to take the look at me, I forgot my plus c, which is important here. And I'm going to make a change here. Well, I'm going to do a new line. T plus 20 plus, and then instead of c, I'm going to call it ln a, right? Now a is just a constant, right? Log a is just they're just constants, they're fine. I suppose the only question you could ask is, could that have been a negative thing? Because that can't be negative. But anyway, I'm not going there now. And so I'll get ln x equals ln of a over t plus 20, right? Just using log laws. That's why I did this, so that I could get that, and then I can anti-log both of them, a over t plus 20. All right, so I've got x and t related to each other, still with a constant, right? So for some constant a. And so now, given the initial data, right, so I've got t equals 0, x equals 20 kilograms of salt initially. So we have 20 equals a over 0 plus 20, which means a is 400. So therefore x as a function of time is 400 over t plus 20. And then we would need to find after 30 minutes, right, we've got x 30 equals 400 over 50, right, which is 8 in units of kilograms. All right, so there we go. 8 kilograms of salt remain after 30 minutes. This is a simple hyperbola, of course. All right, so okay, but of course all of this doesn't really exist, because that is time and that's temperature. No, it's not. It's salt over time. All right, and at 30 minutes we have, so we had 20 kilograms of salt initially, and after 30 minutes we have 8 kilograms of salt, and as time goes on, well, it's approaching 0, as makes sense when you read the question and think about it. Okay, so the time for exercise is over and the time for presentation is over. So I hope that was useful to you, and like I say, I welcome any emails and stuff. There's my details, and there's the link where you can get the slides, and in 5 minutes I'm going to make the scratchings available at that same address. All right, bye-bye.